Yeah, thank you so much for the invitation. It's great to be here. So today I'm going to be talking about our recent work on Plex, which builds on a line of work on scalable probabilistic deep learning, and I'll try to highlight. Also, sometimes people just present the end product in some sense of the research rather than the stepping stones and the motivations. I'll try to give a bit of like the backstory and all the missing pieces and the hypothesis, so that in case it's helpful to folks in the audience here. And this is obviously joint work with lots of awesome collaborators, both within Google as well as Yaron Gul's group at Oxford. Yeah, so I have the links here, so feel free to take a look. And we also have a blog post kind of like describing at a high level, which is a bit more introductory for this. So what is the motivation? So let's, before we, what is the motivation? Why do we care about this problem, right? Like, so the, the, the we want to be able to quantify uncertainty in deep learning, and these slides are from our NeurIPS tutorial a few years ago. You can take a look for more details, but I'll just be concise and give some background. The reason we care about uncertainty is that good uncertainty estimates can help us understand when we can actually trust the model's predictions. So for classification problems, uncertainty means could just mean like not just outputting the top one label, but also an associated confidence score. And for regression problems, it could mean not just outputting like a mean, but say a mean and a variance. It could be as simple as that. So, but at a high level in probabilistic deep learning, the name of the game is to return distributions over predictions rather than a point prediction. And good uncertainty estimates are going to be really useful to know when we can trust the model's predictions. And it's going to become important in a lot of like downstream tasks, as we'll see in the rest of the talk. And the other terminology you may have heard a lot about is the so-called out-of-distribution robustness. So a lot of machine learning was studied in the so-called IID setting, where the test distribution is assumed to be from the same distribution as the training, but this assumption is frequently broken in the real world and lots of challenging applications. And we are now, there's a lot of interest in the so-called OOD setting, where at a high level, OOD you can think of really means as like not IID, and where the test is not the same as train. And obviously we need to make some specific assumptions on like the cases that we typically study. And some examples of like dataset shift are covariate shift, where I'm just trying to give a taxonomy of the types of like OOD shifts that we'll also study in the in like Plex. The reason this becomes really challenging, I really want to drive home the point that this is, I think, one of the grand challenges of machine learning in my opinion. And the reason really being that there's only one way to be IID, but there's countless ways you can be like OOD. And it's really to truly tackle the robustness issue, we really need to be able to understand models that are robust to like a whole different, it's a much more challenging problem. That's what I'm trying to hopefully impress upon you. And some examples of dataset shift are covariate shift, where we assume that P of y given x is fixed, but P of x changes between train and test. The so-called open set recognition setting, where we assume that new classes belonging to inputs may appear at like test time, which are not seen during like training data. And this occurs a lot in like scientific applications as well. So where, like for instance, if you're training like models on like genomic sequence identification and so on, we actually don't know a lot of the classes. People are discovering like new classes at all the time, right? Like, so if you train a classifier based on historic data and try to apply it in the real world, you really need to be not just have accurate models, but actually OOD detection to really enable ML to be successfully applied in some new some of these applications. So this becomes really important in those applications. And subpopulation shift, obviously, where frequencies of data subpopulations change and other things. But this is kind of like an incomplete list. There's a whole people are I encourage you to really take look at this literature. There's other types of shifts such as like label shift and other distributions as well. So this is an incomplete list too, and these are challenging enough on their own, as you'll see. And the reason I think this is really interesting to study is deep learning really achieves, it works really well on like IID shifts, but on OOD shifts, the models are still not as great as we would like them to be. And a case in point is this benchmark you may have heard of called ImageNet-C from this paper by Dan Hendricks and Tom Dietrich, where what they basically showed is that if you take like models which do really well on like ImageNet, the clean test set, so as to speak, and evaluate them on even on like slightly, they need not even be like adversarial, even like natural corruptions, the models start failing. And I really like this data set because it gives you like a knob for controlling the amount of OODness, so as to speak. So you can start with, you can measure the model performance on the clean set, and as you go further and further away, you can kind of like progressively increasing the distance between test and train, you can see how the models fail. And the reason why I talk about both OOD and uncertainty jointly is that the importance of uncertainty becomes particularly important when you have out of distribution, right? Like, so it's inevitable that the model is going to make mistakes when you, as you progressively go out of distribution, but it's important for models to know what they don't know. And so that if they can at least say, like, when they are likely, if they signal in their through their uncertainty when they are likely to be wrong, we can only trust the model, let's say, in the vicinity of the training data, and as they go further and further away, trust the model prediction less. In some sense, that's the kind of behavior, the ideal behavior that we kind of like expect. And we did this benchmark to just like test whether how good is the model calibration for this on this problem. So this plot is from our benchmark paper in 2019, and the x-axis shows the shift intensity. So the typical test has like no corruptions. That's the usual test set, and you can see the model accuracy is here. And as you progressively increase the shift intensity, then the model accuracy starts dropping. But the question you might wonder is, well, if the model accuracy is dropping, but do the models know, is the fact that the accuracy is dropping reflected in the model confidence? So we asked this question to evaluate the performance of model uncertainty as a function of like distribution shift. And we did a large scale benchmark at that time with all the popular methods at that time. And we looked at, in particular, what's called expected calibration error. So calibration error, for folks who are not familiar, you can think of it as some sort of like meta accuracy in some sense. So it really measures the agreement between the confidence, which is the model's predicted probability of correctness, right? So when the model says 80% confident, it says, I think I'm 80% correct. That's its own predicted probability of correctness. And the accuracy is the observed frequency of correctness. You actually measure the ground truth labels, and then we measure whether it's correct or not. And calibration really just intuitively, you can think of it as the agreement between the model's own estimate of its correctness versus its actual correctness in reality. So we would ideally like these to be aligned very well. That's called a calibrated model. And one way to do this is to measure what's called the expected calibration error, which is just really binning the probabilities and measuring this discrepancy between the two. One of the surprising things that we found in this paper was that the model calibration also gets really worse with distribution shift. And this is kind of like a problem because the models are making more mistakes, but they don't know that they are making more mistakes. So it's really hard for practitioners to know when the model, say, gives like a 80% probability, should you trust it or not, right? Like, so, and for safe deployment, this is a big problem. This is what we mean by, like, neural nets do not know when they don't know. And that's a problem we want to fix. So ideally, we would want this line to be as flat as possible, so that if there are calibrated estimates, you can leverage the uncertainty to decide when to trust the model or not. And the other problem I also want to highlight, like the other, go back to the open set recognition that I kind of like briefly touched upon. And in open set, the fundamental issue is that the models may produce high confidence predictions really far away from the data, even on like classes. If you train like a classifier on like MNIST, and then you show it like pictures of, let's say, fashionableness, which are completely different semantic classes, it will still give like very high confidence predictions. And that's really at the heart of the open set recognition problem. And you can construct like really simple like 2D examples like this half moons example, where if you visualize the confidence landscape from this neural net, what you see is intuitively, if you're familiar with like, like tools from like probabilistic machine learning, like Gaussian processors and things like this, you might expect to see the model confidence be really high in the vicinity of training data, and as you move further and further away, naturally the model should become less confident. But if you plot the top one, the confidence associated with the top one prediction, here you pretty much see that yellow means close to 1. The model gives high confidence predictions pretty much everywhere across the board, and even on like even if like some test data like this, like imagine this red cluster being like a completely different class than these two moons in the original training set, the model still gives like high confidence predictions to this. And you can construct this toy behavior even on like really, it's not a matter of like dimensionality or other things per se. It's really more about like the inductive bias in neural nets that we should really think carefully about. And so hopefully I kind of like laid out the motivated the problem of why uncertainty and OOD robustness are key. So the past few years, a group has been thinking a lot about how do we really make progress on this. And like I mentioned, one of the key challenges is that we don't want to. What do we mean by a reliable model? Because there are so many different aspects and dimensions to this problem, that it helps to kind of like take a step back and really think about what are the key properties that we want from machine learning model, right? Like so. We thought a lot about that and tried to design like a comprehensive benchmark that kind of captures the essence of this problem in some sense. And this is what we kind of came up with. It's incomplete, obviously, and I'm open to suggestions and hearing your thoughts. So roughly the way we kind of like thought about like reliable model, what does it mean for a model to be reliable, is that we kind of focus on 3 separate dimensions, and I'll talk through them one by one. So the first aspect is what I call robust generalization. And this kind of like going back to this example of like ImageNet versus ImageNet C, we want the model to generalize really well, not only on in distribution, the IID set, but also covariate shift. So because under covariate shift, there are not like new classes, so we want the models to fail gracefully and be as accurate as possible and really learn like robust features. Basically, the assumption is that the models which don't do like shortcut learning and really learn the true causal features and robust features are expected to be like more robust. So that's one part of the problem. Like, how do we generate models that generalize well under different types of like shifts? And it's really important to stress test across different types of shifts, because there's no one OOD. It's really important to keep the back of your mind. There's only one IID, but there's no one OOD. And it's really important to stress test across covariate shift, subpopulation shift, and across many different types of like distribution shifts. So we want the model to be as robust as possible. The next step that we want is, in the real world, it's inevitable that the model is going to make some mistakes, right? Like eventually, it's very the model is going to be asked to make some predictions where it's likely to be wrong, or on like this open set setting and like other things. And that's where the uncertainty piece of the puzzle really comes in. And we can measure uncertainty through many different ways, but some key dimensions that we can like think about or calibration, selective prediction, where we ask the model to maybe like abstain and give the model an option to defer its prediction to a human expert or to another system or something like that. But basically, we use the model uncertainty to decide whether we should trust the prediction or not. That's the task of selective prediction. And there's also the task of like open set recognition, like I mentioned, where new classes may appear at test time. So imagine you trained a classifier on like CFA10, and at test time somebody shows like an image of like SVHN or some other different class that's not in one of the K classes that were in the training set. Is the model able to accurately detect that? It may not be able to correctly predict the class, but you should at least be able to say it's none of the above, right? Like, so that's one of the hallmarks of human intelligence. If you for instance, if you show humans like characters from a language that they don't speak, I speak only 2 languages, but if you show me characters from a language that I don't speak, I may not know what those characters mean. I mean, in the sense that I may not be able to correctly classify them, but I can say for sure that, okay, I don't know what these are, but these are definitely not English alphabets, right? Like, so I can say that for sure, and that's the kind of like property that we want from our AI systems as well. So that's the task of like open set recognition. And the other aspect of uncertainty that we also care about is label uncertainty. So the reality, if you even look at like, there's a really nice series of recent papers on even showing that on ImageNet, there are like multiple classes that may be consistent with the data, and we really want the model to capture the whole distribution of like prediction. So sometimes the model may contain like multiple objects, or it could be a bit ambiguous where 2 answers kind of like make sense. And as we go towards more like this open-ended systems, or like large output spaces like ImageNet, even like in 1,000 classes, there's a lot of like ambiguity, and sometimes multiple labels may be correct. We want to model to capture the entire label uncertainty there. So this is what we mean by building models that know what they don't know. The final part is in real world deployments, the uncertainty may be an end goal for some applications, but for other applications, they really want to go one step further. So like in academic datasets, typically we study, like, in research, we study more like static datasets, but in real world applications, the datasets are not really static, right? Like, so the models are being continuously updated and so on. And it's important to be able to quickly update the model and kind of like learn what the model doesn't know in some sense, and to do so in an efficient way. And you may be familiar with like tasks like active learning and so on, where we can leverage the model uncertainty itself. So if we had a sense of where are the regions of the input space where the model is uncertain, we could get more labels in that region to quickly update the model in those, which can be much more effective than, say, random sampling, which might end up resampling data from the same regions where the model performance is already good. So to put these 3 together in some sense, so these are like the 3 dimensions of reliability that we kind of like stress test across through multiple tasks in some sense for the model. And the reason why I also kind of like pitch this as an overall goal is that sometimes we might end up focusing on one particular aspect of this, and there are some methods which in the past where maybe like some people have, and myself included, where we felt like we may improve like one dimension of this, but it might actually end up like hurting like other aspects in some sense. And whereas in real world deployments, usually they care about multiple of these cases. So that's why we try to holistically look at what is to give you like an analogy. Like in, like one of the big trends, and I think like in NLP, which really drove the field forward, was like trends moving away from like narrower tasks to more general purpose tasks, which really pushed the field forward in terms of like the foundational techniques and what are the principles that end up the key principles that end up improving the not just a narrow task, but like overall task, right? Like, so if you think about like narrow narrow reliability versus say more general reliability, we believe that this metric and the techniques that kind of like push these forward are going to be more valuable and useful generally. Right. So I'll probably stop there and take any questions if anyone has questions.
Any questions so far? There's a question. Yes, go ahead.
Oh, I can't hear you.
A little bit louder, please.
There was a bar plot in the previous slide. What's the variability across?
Could someone repeat? Oh, okay.
If you go to the previous slides, there was a bar plot, an error bar plot. I just wanted to ask what was the variability across?
Oh, I see. That's a good question. So for this, for ImageNet C, it's not just like one form of corruption. The paper introduced multiple forms of corruptions. So for each intensity, it's actually averaged across like many different forms of corruptions, like like different types of noise, different type of like blurring, and like other things that are added. So the variability is over the different types of corruptions.
Thank you.
What is the base neural network you're using here? Which network?
So for the background, the motivation, I mean, this plot specifically we use like ResNets, but I think the overall trends to generally translate, and the Plex work that I'm going to be talking about is all built on top of transformers, vision transformers for vision and T5 for text. Yeah. But a lot of the phenomena that I am talking about are not really architecture dependent. You could reproduce this with like MLPs, coordinates, transformers, any different backbone. Right. So let me jump ahead to the next part then. Let's switch ahead to the specific paper that I'm going to be talking about, our recent work called Plex. And the setup, the reason why I'll talk more about like the ingredients and why exactly we ended up with the setup, but the motivation was we had a bunch of papers last year from our group showing that pre-trained models in particular really improve the calibration, some of the narrower tasks, right? Like, so we focused on more narrower tasks, and where we found, like, for instance, pre-trained models are really good at calibration under shift. And we also found that pre-trained models tend to be really good at open set recognition on some of the vision benchmarks that we've been kind of like using. And then we thought, okay, let's take a step back. And one of the holy grail problems in some senses, like a simple recipe that works well across all tasks. And we thought, okay, let's start with the pre-trained models as like backbones and see whether we can, how much we can really push overall reliability as a goal. And so the setup we are going to be using is we take a pre-trained model, which is pre-trained on like a big data set, typically ImageNet 21K GFT for vision and C4 for text. And we are going to fine-tune the model on the specific data sets, such as like, ImageNet. And then we are going to evaluate on multiple downstream tasks. So I mentioned like a whole bunch of tasks around focus. Some tasks are focused on robust generalization, some tasks are focused on like uncertainty quality and so on. And in the end, we are going to aggregate all of the scores to kind of like get like a final reliability score. And we also have like more fine-grained analysis in the paper that I encourage you to check out. So in terms of like more details, we consider like different scales of like inputs to kind of like test the input data set scaling for the models and show that the techniques do really scale to the really large model classes. And we fine tune on multiple different data sets to do some more fine-grained studies on the questions. And the eval set, so we fine tune on these specific data sets, but we eval on like a different set than the fine-tuned set itself. So here it's the pre-train is you pre-train on a more like general data set, and the fine-tune on like a very specific task, and then you evaluate the model robustness using like a different, which is out of distribution for the fine-tuned data set. So like different sets, such as like different variants of like ImageNet OD sets, and so on. And we have different tasks. For instance, like retina for like country shifts. So retina is a diabetic retinopathy dataset from the previous retina paper. We constructed like this ImageNet real H for like human, which contains like multiple human labels per class for label uncertainty. And we also do when we fine tune on like CIFA10, because there's a lot of like academic benchmarks on this problem. We also measure on the setup where you use CIFA10 as the in distribution and Street View house numbers as the out of distribution dataset, and so on. And we also have other datasets for subpopulation shift and adaptation. For language, we do a similar setup. We pre-train on C4, and we consider like different sets of tasks, such as like NLI, toxic comment detection, and other tasks focused on natural language understanding. So conceptually, it just to make sure that like the methodology extends to like different modalities and different backbones. Both are transformers, but there are slight differences in the setup and the tasks between language and vision. We wanted to make sure that the recipe that we develop translates to both across modalities as well. So we consider, like I said, we consider like different scales of models to study like the scaling effects, like small, the typical base model and a larger model as well to study the scaling effects. And we use vision transformer for our vision experiments as the backbone, and T5 for the text experiments. So the key ingredients that I'll then next spend a bit of time talking about the key ingredients. And there are two classes of ingredients that we primarily focused on. And this builds on our line of work from our group the past few years. And I'll spend a bit of time talking actually a bit more detail into these two classes. The key parts are for large models, a lot of the techniques that we used to do don't really scale well. So we really focused on two different class of like scalable probabilistic deep learning blocks, namely efficient ensemble blocks and what's called last layer models, which are basically you keep the representation, you just change the last layer from the typical dense layer to something else. And I'll talk a bit more into detail, about the specific methods that we used for these things. So the first method I'm going to be talking about is motivated from our paper called Spectral Normalized Neural Gaussian Process, or SNGP. So SNGP, we wrote this paper a few years ago on, and it was really focused on how do we build like better building blocks for probabilistic deep learning. So in some sense, if you put your Bayesian hat on, there are kind of like multiple ways to capture uncertainty, right? Like, so there is p theta of y given x, and you can either do like better marginalization over like the thetas, or really think carefully about like p theta of y given x and see how far we can push like the model uncertainty from like even like what's called a single model, or this is also called deterministic uncertainty quantification. In the sense, the reason for the being, if you use like a single representation and you just marginalize over the last layer, so this is kind of like using a deterministic representation, but just marginalizing out the last layer. And from if you think from a compute versus quality of uncertainty perspective, this is very effective from this point of view, because it typically, the forward pass is the more expensive part. It's just a last layer method. So these are very fast and easy to implement, and they don't add a lot of compute because it's just literally replacing just the last layer. So these methods are very efficient in terms of like both inference time and memory, and they tend to improve the quality of uncertainty and robustness. So specifically, I'm going to go into the details of SNGP, but the problem it's trying to solve is the problem that I initially spoke about. If you look at the confidence landscape from a DNN, the vanilla model can assign high confidence predictions far away from the data, going back to the sophomores example, and we'll show that SNGP actually allows us to get like Gaussian process like behavior, where we get the concentration of the model confidence with in the vicinity of the training data, and the model naturally assigns low confidence predictions as we move further away. And I'll describe how exactly SNGP does that. So to understand SNGP, it makes sense to think about neural nets as kind of like two steps. So if you think of like a typical neural net, there is a feature extractor which maps from x to some hidden space h of x, and then there's a dense layer on top, or right, like the last layer, the layer just before the softmax, there's a dense layer which eventually generates this p of y given x. SNGP makes two modifications to the setup. So the first is it replaces this DNN with it actually does not change the architecture. It just adds regularization to ensure that the model learns smooth representations. So this is just like adding like a regularizer to ensuring that these representations are smooth, and it replaces the last layer with what's called the Gaussian process last layer, and I'll go into the details of how exactly this works. So why do we do this, right? Like, so let's take a step back and try and understand why do vanilla DNNs assign high confidence predictions far away from the data. So using the description that I just mentioned in the previous slide, let's think of neural net as mapping like x to h of x and dense layer on top. There are kind of like two problems going on here in like a typical neural net that leads to this behavior. So the first problem is neural nets can do what's called shortcut learning, whereby the model ends up mapping points that are quite far away in input space to very close points in latent space. So for instance, if you look at like this example, what happens is the model ends up mapping the bottom quadrants to very close points in like latent space. So the red cluster ends up being very close to the orange cluster, even though it's quite far away, right here. And this is actually okay in the IID setting, right? Like, so if the model just expects to see data set from the same distribution as the blue and orange, it may not learn causal features, but in the IID setting, these features may be okay because if it's just getting these models, it may still lead to the correct prediction. But the problem is when you expect to have some sort of like out of distribution, the model might end up actually mapping these red clusters to very close points in the in latent space, and that's a problem. So this is what people call like shortcut learning and feature collapse and like various different terms that are related to this phenomenon. The second problem is that we are using a dense layer, and the inductive bias of the dense layer is the following. So think about, so this is basically doing logistic regression, right? Like, so if you freeze the features as a function of these h of x, the dense layer is just doing logistic regression, and it's kind of like a linear, what statisticians call like generalized linear model. And the nature of the probability output from this is that the confidence happens to be a function of the distance from the boundary and not the data. So, and this distinction becomes important in the presence of like OOD. And that's really why you see what's happening here is the model is really only uncertain in the vicinity of the boundary itself, which is literally this boundary. That's where the model gives uncertain predictions. And on points, if there are points that are far away from the boundary and far away from the data, the model unfortunately gives like very high confident predictions on these parts as well. So so this is what we, in the paper, we motivate this as models are not like distance aware, in the sense that the models end up assigning high confidence predictions to points that are really far away from the training data. And the solution we kind of like proposed in this paper was to encourage like smooth representations. And one way to do this is if you don't have any other inductive bias, you can do this through spectral normalization, which is a way of enforcing bi-Lipschitz smoothness. And basically, all this really says is bi-Lipschitz smoothness literally controls the Lipschitz smoothness in both directions of this mapping, which ends up ensuring that points that are far away in input space or end up getting mapped quite far away in like embedding space as well. So for instance, this red cluster getting mapped quite far away from the orange cluster. So that's one way. It uses this ingredient to prevent this shortcut learning. The other ingredient we use is the Gaussian process layer, and we use a really scalable implementation of a Gaussian process layer. And we use, if you're familiar with random feature approximations, they're actually really efficient because it doesn't scale with the input points n, it just scales with the number of like random features, and it's just quadratic in the number of like random features, so which is way more efficient than the like typical GPs, which are thought to be like cubic in the original number of data points. So, and we just use Laplace approximation, which is quite simple to implement and really scalable that you can do. So the behavior of a GP layer just on the last layer is that the GP confidence concentrates in the vicinity of the data. And in the original SNGP paper, we used both of these ingredients. I just wanted to highlight this in case you're thinking about applying this to like other problems where you may not be able to do pre-training, for instance. But for the purpose of Plex, we just use it in the last layer. And the reason being that, just going back to this slide, the key phenomena that we want is the models to not map points that are quite far away in like input space to very close points in like latent space. And when you pre-train on a diverse data set, such failure modes are less likely to happen anyway. So the once you have some amount of separation, the GP can work actually quite well. It's only in cases where the pure GP approach fails if you have phenomenon like this, because the GP ends up being only as good as this. So we just ended up, for Plex, we just ended up applying it on the last layer here because the pre-trained model representations already prevent collapse to some extent.
Can I pause you and get some questions?
Sure.
A couple of questions. So when you're basically training, very interesting, in fact. So, but when you're training using a bi-level Lipschitz constraint, it means that if you have samples that are far away from each other in the pixel space, in the input space, you want their feature representation to also be not to be too close, right? So you don't want like the collapse of their features. But wouldn't it prevent us training models, for instance, on images? Because like you may have like, you know, images like images of cats that are like extremely different in the pixel space, but in the feature space, we want them in fact to be close to each other.
Yeah, that's a very good question. So what we actually ended up implementing in the original SNGP paper, for instance, was we added spectral, we added a variant of spectral normalization to avoid constraining this feature space. So I think like my intuition is that we want some sort of like near invertibility, but not like perfect invertibility in some sense. So that because that would put somewhat a harder of a constraint, which actually is not really needed in like practical applications, and that might end up also hurting the accuracy of the model. So we do near invertibility, which is not the key property that you really want is points belonging to really different semantic classes end up mapping close. So the pixel space, because we do it on top of like nets and so on, they naturally have this invariance. So we don't apply spectral normalization to those layers. The key effect really happens in the fully connected layers and so on of the network, where it prevents the weights from blowing up, which in turn controls the Lipschitz constant. And we found that to actually not hurt the accuracy of the models. And so it's kind of like, it doesn't change the accuracy, but it improves ECE, OOD detection, and all the other metrics.
And my second question before I get the students' questions is basically for the second part, you can observe a similar behavior even for SVMs or linear classifiers, right? So you have a decision boundary, and let's say you have some samples, you learn the decision boundary, and the samples that are like far away from the decision boundary, let's say on the right side, then they will be assigned to very high confidence. So basically, you know, is your argument that even like on those models, it is better to not, you know, have models to assign the super high confidence to those tail samples either on either side of the decision boundary?
Yeah, that's a great question. So it's true that even SVMs would do similar behavior. I think my argument, I would say, is that like some of these ideas were originally developed in the IID setting. They weren't really thinking about this OOD setting when they developed like some of these principles, right? Like so I think in the presence of, as we move more towards OOD, we may have to rethink some of these principles and the assumptions that we sometimes take for granted. And I think this is actually one of them, in the sense that, like, even the feature collapse, like I mentioned, right? I mean, if you did a SVM, it would probably do something like this in some sense. And it's not wrong in the IID setting. So it's just, I'm not saying it's wrong. I'm just saying it's incomplete. As we move towards OOD, we may have to rethink this abstraction of how what is the implicit assumption, like exactly what I said. If the test is going to be distributed exactly from the blue and orange clusters, right? Like that's the IID setting. This is not a bad thing to do per se, because the model, maybe it leads to actually some efficient classifier, because the model ends up mapping the complete bottom two quadrants onto very similar points in latent space. So it actually learns a very efficient feature in some sense. But the problem is when you expect to have some amount of like distribution shift where maybe like there are some other points which are like this red cluster which may not belong to this orange, and in applications maybe this distinction is important to say for as we move towards like this OOD setting. This may not be an inductive bias that we actually want in the model, that going always further away should always increase the confidence necessarily in some sense. That's the kind of like argument I'm making.
Very interesting. So let me see if there are questions from the audience. Okay, I think clear. So no questions.
Yeah. So we use this GP layer, and we also actually consider this heteroscedastic layer, which gives input dependent, which captures input dependent label noise. And the way to so the original paper that introduced this basically what they did was they replaced the dense layer with what they call the heteroscedastic layer, and this captures label uncertainty because it models the logits as like through this specific form where they capture like the interactions between like the different classes, and they show that this in turn induces a distribution, effective distribution over the labels, because this covariance matrix captures the confusion between the different classes and which of the classes kind of like co-occur. And if you do this, this ends up giving a much more richer distribution compared to the vanilla model, which does not capture this distribution. And so this was the original heteroscedastic paper, but in our group, we also kind of like extended the combination of the two. In some sense, we call this like het SNGP, which so you can think of SNGP as producing a better estimate of the mean in some sense, and the heteroscedastic as capturing the covariance, the noise process, which eventually leads to the final decision. And you can combine the two, and depending on the downstream task, different variants may end up being like more helpful. What we found is for like large vision tasks, the het variant, the variant which captures more on the heteroscedastic part ends up being like more important for really large output spaces. Whereas for text experiments, for instance, where we have the domain shift becomes like more important, and there's not really as much like label noise per se in these tasks. The SNGP part becomes more important for accurate OOD detection and so on. But I just wanted to mention there are this line of work on combining these two, capturing these two sources of uncertainty, as may have heard about, like, epistemic and aleatoric uncertainty a lot in like other work if you're looking into the literature. So the other ingredient I'm going to be talking about is ensembles, and efficient ensembles in particular. And as you may know, when we did this, so one way I like to think about this is, so there's a single model. Oh, I don't know why it didn't render. Okay. There's a single model, but you can, SNGP approaches try to start with a single model and try and push the frontier along this axis. So that's the, if you think about like ideas for improving uncertainty, they do this improving the base model angle, but there's also another way to improve the overall quality of uncertainty, which is efficiently averaging over multiple representations. So in deterministic uncertainty quantification, we focus on, we ask the question, given one set of representation, how do you kind of like, efficiently get uncertainty? And the way to do it is marginalizing over the parameters of the last layer, because that's really the only thing you can do in that setting, or capture the label uncertainty by inducing like a noise process on like to model the human confusion between like the classes and so on. So those are the family of approaches. Here we ask a different question: how do we efficiently get like multiple representations between this? And you can think about making it both. Our team has done a lot of work on both adding like diverse ensembles as well as like making them more efficient, and you can think of them as moving on different points along this curve in some sense. So It's funny. I don't know why it didn't render, but basically one of the popular baselines for uncertainty quantification is what we call deep ensembles, and even in the benchmark that I showed you earlier, the can you trust your model uncertainty, one of the things we found is that um, ensembles tend to do really well, and the just like retraining with like multiple random seeds and combining the models. But obviously, for really large models, this is not feasible because this tends to be very expensive. So we don't really want to do deep ensembles, which motivated another line of work on how do we kind of efficiently generate ensembles of models. And you may be familiar with like ideas like dropout, Monte Carlo dropout, where we use like dropout masks to construct like different ensemble members, and we use this what's called batch ensemble or a rank one ensemble from this paper. And the key idea is that it constructs different version of like ensemble members through rank one perturbations. So the way to think about it is you eventually want to create like two different weak matrices for different members of your ensemble. But the way you do it is they use like a shared matrix W, and then they just do like different rank one products. The only difference is between these two models is that the rank one product, the R and the S parameters, so the row and the column weights. And this rank one matrix, because it's very parameter efficient, because you're just generating like the rows and the columns, and this leads to more diversity between the members. So this is a way to construct efficient ensembles. And we have some work also showing that from a loss landscape perspective, these tend to be more diverse, hit like different modes in like function space, have like different more diversity, which ends up being helpful for uncertainty quantification. And another way to think about this is in dropout, depending on whether you apply dropout in activation or weight space, you might end up perturbing it only either if you apply it, say, on the activations, you might just end up applying it here, or if you put up the weights, you may just end up applying here. Whereas the rank one is a very efficient way to perturb both in some sense. So that's another way you can think about this rank one ensemble. And this is very scalable and applicable to large networks. So we use this as the other building block. Are there any questions?
Oh, let me see any questions.
Okay, I'll try to wrap up in the next few minutes so that I can take other questions later. But so basically what we did is for vision transformer, we took the backbone, VIT, and then we also consider ablations like, do you apply ensembles just during pre-training, just during fine-tuning, or both pre-training and fine-tuning. We have some ablations showing that. And we also considered like different variants, but the one that ended up actually working a lot well for this task is using ensemble blocks and the heteroscedastic class layer. And for T5 Plex, the ingredient that ended up working well was batch ensemble plus the GP class layer. And you can basically think of these as like special cases of HTS and GP layer in some sense. It's just with different hyperparameter tuning. If you had tuned the hyperparameters and found the best one, both it would just end up with the same recipe, just with a different each of the tasks emphasize slightly different aspects. And I think that's why this approach ends up working best in the end. And so we have some results here, and we kind of like present it using these radar plots for both on vision and on text. So the way we kind of like present it is like there are different tasks, and the red shows the individual state of the art on some of these tasks before, and the blue shows the performance of Plex. And I think the part that I'm really excited about actually is the fact that the different red points are actually models which are specialized to like specific tasks, whereas Plex is just like one model, and we measure the out-of-the-box performance. So we don't do any custom tweaks, like for instance, like anything special just to detect like OOD inputs. And of course, you could squeeze a bit more performance on the individual tasks if you do something specific to like each task. But we wanted to really see like if you just develop more like a general purpose recipe for reliability, how far does this map and scale it up to like large models? How far does this map? and you see that it does really quite well, and that to me is like very exciting. And the same recipe kind of works really well on, and you say the similar trends on language as well. And I think like that part is very exciting. There are still some places where it doesn't do as well as a specialized as you might expect. So what we have found is, if there is the more distribution shift that you have, like for instance, JFT versus say like more diabetic retinopathy images, which is somewhat a very narrow task. For narrow tasks, you can still get more by just like fine tuning on that specific data set and developing like custom models. But I believe if we scaled up this model to like a more even more data set and be more careful in how exactly we fine tune for the setups, I think we can, there's still some work to be done, but I think we can, I believe we can close this gap even further, even in those cases. So we also show like, tasks for like specific tasks, like I mentioned, like selective prediction, where we look at what's called the collaborative performance, where we look at, we assume, for instance, if the model is uncertain, we assume it's deferred to a human who, if we assume that they will always get it right, and then we measure the collaborative accuracy. So the task measures whether the model correctly abstains on cases where it is likely to be wrong, because that's where the overall collaborative performance really will improve in those cases. And here we do see that depending on if it differs 2.5% versus 10% and 20% of the inputs and so on, and we do see that it really improves the overall collaborative performance. And we also do tasks like more structured open set recognition. So for natural language, we actually considered like more hierarchical forms of like OOD. Like for instance, typical OOD would just consider one aspect, but here you can imagine like if the model asks like a question, the user asks a question like this, like, can you make 1, 2, 3, 4 a pin for my savings account? If the model might detect the vertical correctly, it might understand that it's actually a question about bank. It's just not supporting this specific intent. It maybe just not allowed to change the pin. It can allow more nuanced customer responses than just saying, I don't know, for all tasks. And I think that's kind of like really interesting for the next generation of systems. And we also consider some results for zero-shot open set. As you may have seen, zero-shot getting a lot of attention, and we also evaluate performance. And there are some tasks where it actually they are quite challenging because visually they look actually quite similar. Like these kind of like sea horses in like water versus like birds on top of like actual sea. Some of these examples, if you look at the closest examples, these tend to be like quite hard. And even like the rainforest versus like a zoomed in version of a flower pot, or like florist shop versus like a specific type of like fungus and so on. So they visually look quite similar, but the model is able to correctly detect these as OOD, which is kind of like really interesting to see. And we also looked at this label uncertainty. So like I said, there are some cases where like if you ask the ground truth labels, it would be a distribution. It's not just like a one hot ground truth label. Human uncertainty would put like mass around like multiple classes, and we see that our variants are able to capture that uncertainty as well. And we consider, we actually see really big gains in like active learning, and much of the gain actually comes from pre-training. Obviously here, it's just to show that if you apply the uncertainty ideas and a lot of the probabilistic machine learning ideas on top of pre-trained representations, they tend to do really well, and we see like really big gains in terms of like active learning accuracy and so on. So we have a lot more ablations in the paper, so do check it out. In the interest of time, I'll stop here and just point out that we have code if you want to play around with. We have some demo collabs. I encourage you to check it out. And yeah, I'll stop there. Thank you.
Fantastic. So let's thank Balaji. So we have time for a few questions. So I'll just like start with my own question. So how would you compare the performance with like some of the other models trained on like multimodal data, like trained on image and text, for example, clip, Do you expect, Plex to outperform them in some of these OOD tasks, or what is your take on that?
Yeah, great question. So I think I mean, Plex can be extended to multimodal models as well, right? Like, so it's more the backbone. We consider this for like unimodal models, but for multimodal models, we can extend the same ideas to multimodal models as well. What we have seen we have done some experiments in like other papers. I can give pointers offline, exploring like multimodal models and so on. And we do see some gains in like across reliability. So we do expect models to be more reliable, multimodal models to be more reliable. Yeah.
Yes, go ahead.
The OOD and the zero-shot results from the Plex looks actually really impressive. So I was wondering if you tried checking if Plex is kind of reliable under various attacks like adversarial examples.
Yeah, that's a great question. So that's actually one area where I haven't actually done a lot of work. So I think that investigating adversarial robustness of these ideas is actually a really interesting problem. And I don't have a lot of expertise in adversarial robustness per se, and I do think some of the ideas. This is something I've been kind of like wondering whether, like even the even if you going back to this SNGP collab, right? Like, so if you remember, I think it was the follow-up paper from Ian Goodfellow and others, the explaining and harnessing. So they had this argument around like RBF networks and adversarial examples, and I keep thinking maybe like if we use this as a building block for adversarial robust, that's one part I actually wondered a lot whether this would actually end up improving adversarial robustness. I don't know the answer to the question, but I think it'd be very interesting to investigate that question.
Yes.
So you mentioned that after you regularize the continuity, when you impose continuity on the layers, it learns a representation that is nearly invertible. So is there a sense of how invertible it is? Like, is it?
Good question. So we didn't quite exactly measure this, but we did measure some sort of like and this is going to be a bit hand-wavy. It's not precise, but I'll tell you like a lot of the empirical phenomenon. Maybe somebody can actually answer. The short answer is I don't know the answer, and I don't know whether anybody has actually tried to quantify this precisely. But I think it'd be a very interesting question to kind of like investigate more in detail. And my experience is, so I actually worked on something called hybrid models before, on top of like like flow-based models, basically trying to use like flow as a feature extractor to construct like a more robust model. And one bottleneck that we kind of like hit upon there is that it ends up being it works well on like MNIST scale, but even if you go to CFAR 10, you already start seeing like some gaps between the performance. And if you try to push this to ImageNet, you really start seeing the gaps in the accuracy and so on. So perfect invertibility is kind of like hard. But if you follow that line of work, there is some nice work from Toronto where they actually they don't use the exact flow. They use some sort of like ResNet like building blocks, and then make it just like near invertible. And they show that this actually works really well in terms of like accuracy and like other tasks. And I see SNGP as somewhat motivated by the same insight in some sense. You don't need perfect invertibility. The really important part is to avoid like points that are really far away, not get collapsed, because that makes the GP fail in some sense. Because if the embeddings get mapped too close, the GP can't really undo this. So even if they are slightly well separated, the GP can actually kick in and do a reasonably good job at separating these. But this is the intuition that I have on like the near invertibility part. So so what is the question in some sense is what is the inductive? How can we add this kind of like near invertibility inductive bias to networks such that we don't don't hurt model accuracy, but still have this kind of like separation? And if you can have a way to quantify that and whether to see whether this near invertible measure that translates, that would be very interesting to look into that.
Yes.
The radar plot compared to the data model. Wondering what's the scale of the data? Are the implemented coming from scale?
I can't hear the question. Could someone repeat that, please?
Can you repeat your question with the microphone?
I'm just wondering the difference between scales of data for previous they are not comparable.
So the question is about the comparison when you show like the performance of Plex with the previous state of the art, and the question is about the scalability.
Scale of the data. Like, are they comparable?
Like scale of the data. If I understand, basically the question is like Plex is like on how many data samples, compared to like some of these state-of-the-art models that are perhaps not trained on as many samples as Plex. So are they comparable? So
yeah, actually we have a lot of ablations even within Plex to kind of like answer that question. So you can I hope that would answer the I think I can show some examples here. So for instance, like all of these variants are trained on the exact same data, so you can actually see which of the ingredients kind of like impact the overall reliability and what contributes the most. So you can kind of like compare it through here. There are like for instance here, like I told you, right? Like, so this is like a clear case where it's not trained on the same amount of data. So if you this is just trying to do active learning from scratch, and obviously a lot of the gain actually comes from pre-training. So I guess the point I would say is building these ideas on top of like pre-trained models ends up making, I mean, this is not as interesting, because if you use this many examples and the model accuracy is still like close to 0, it's not very interesting for active learning. But I guess the point is, if you apply this, and you can still get a reasonably decent model on ImageNet if you apply these ideas on top of like pre-trained models. I guess that's the point I'm trying to like underscore. This gives pre-trained models there's an opportunity to make them much more reliable quickly. That I guess that's the part I wanted to highlight. Yeah.
Just to reiterate on one part of the question, because in Plex there are multiple components in play, right? So you have like diverse inputs, and you have different regularization on your model architecture, and the last layer, and the way that you train. So which of these components are the main source of your robustness gain? So is it or coming from this randomization that you have at the end?
Yeah, that's a great question. So I think what we have found is the baseline model that comes from like pre-trained model that gives the bulk of the gains. So if we talk about like the ordering of the overall gains, what is the biggest delta? So I think the biggest delta comes from pre-training, obviously, because data is the biggest differentiator. And this was I didn't spend a lot of time talking about this here but there's 2 papers from our group, like one on what's called exploring the limits of OOD and revisiting the calibration of neural nets. And both of these actually show that pre-training already improves pushes on these tasks quite significantly. So on the individual task. So I think like that's a key insight. And amongst this, to answer the part 2 of your question on like which ingredients impact which downstream task, what we found is for the OOD related tasks where the important part is like to really be able to distinguish points far away from the data, the GP variants actually tend to do really quite well on those tasks. Whereas if some tasks just care about, like, for instance, the accuracy of the model, like robust generalization. So for that, ensembles tend to do quite well because GP does not improve the accuracy. It just changes the nature of it does not change the top one prediction. It just changes the associated confidences and gives it improves the uncertainty metrics, but it won't improve the accuracy. So the accuracy gains come from the ensembling part, and the uncertainty gains come from the nature of the landscape. And the important part is that these two ingredients are actually composable on top of, like, pre-trained, and they really scale well to pre-trained models. And that's the key part, I would say, like in terms of like the ingredients for reliability. That's the way I kind of like think about it.
Fantastic. There's a question from a Zoom audience. It is asking, how well does model confidence predict the accuracy on OOD dataset for SNGP?
Good question. So we, in the original paper, we actually have, I don't have the results here from the original SNGP paper, but you can check that out. I'll also add a link. We have a follow-up version. We wrote a journal version of the paper, which kind of like addresses that. So you can take a look. We add the link here. So that addresses this question. It actually really improves calibration and OD, and it's similar in spirit as well. So we wanted like a simple method that's a drop-in replacement, but also improves all downstream metrics associated with it. And in that paper, actually, we have some insights. I think like this figure in particular actually talks about what maybe also touches upon this question that I don't know if you can see my screen, but this figure on the two ingredients, in some sense, this is not on top of like Plex, but this figure is from figure 2 in the paper. In case you can't see my screen, actually talks about the two ingredients on like the GP layer versus the representation diversity, and how it changes the confidence landscape for these cases, which could be like interesting for people to understand.
Fantastic. Any other questions? One more question. Yes, go ahead.
Yeah, so in case of multi-system setting, since we are using completely different set of modalities, for example, audio and image, or audio or text, so how do these sort of models which are dealing with IID and OD settings, they scale for this multimodal setting? And how different in a way they compose the how different way they approach this multimodal problem to a single problem, a single modality problem where we're only dealing with image data?
Yeah, that's a great question. So I think like the short answer is there's a lot more design choices, right? Like, so there is like image text as input to predicting some quantity in the end. There's like image to text and text to image, and different kinds of, like, even within multimodal, there's a huge taxonomy of like different types of tasks and so on. So the specific setup of what works best would kind of like depend on I believe on the specifics, but the principles more broadly of, like, what would be like helpful is my hunch is that if you did, like, for instance, some of these scalable Gaussian process layers could end up being helpful for improving, like, calibration of conditional language generation models, as well as maybe the ensemble part could end up being helpful for other aspects. I mean, you could use that since it improves accuracy, even if you don't really care about uncertainty, those blocks can end up improving the top one accuracy for those cases. So it can be helpful. But the specific ways of combining this is still like an open question. I think there's a lot of interesting work to be done for multimodal models.
All right, let's thank Balaji one more time for such a great talk.